All right, hello. Hope everybody's staying safe. We know we've had some uh, winter weather and snow and ice going on, so I hope everybody's staying warm, staying safe, staying off the roads as much as possible. And today, since you do have a lab outstanding that hasn't been turned in yet, I'm going to try to keep the lecture today relatively short. But I do want to cover one topic today, and that is communication between threads. So far, what we've done as a quick review is we've looked a lot at thread synchronization, which you have, whenever you have concurrency, you've got different things going on at different times running through at potentially different rates. And like we said really early on, like lecture 1, you can't really make assumptions at how fast things will progress when you're dealing with concurrency. That once two things are concurrent, they're going to run at whatever rate they run at, and there might be things that cause one thread to run faster or slower than another one, but you can't make any assumptions that I'll start these at the same time, so they'll finish at the same time. Or I'll start this one first and this one second, so this one will get to some place before the other one. And so you can have those race conditions, or you could have things like a mutual exclusion that gets violated, where two things accidentally access something at the same time when you don't want them to, and you end up with a corrupted value or a result that's incorrect. And so we've looked a lot at synchronization and the kinds of problems that require synchronization. And synchronization can be thought of as a simple form of inter-thread communication, but we're not really passing data items between things. Really, you're not saying, hey, here's a piece of data. Now, we've done that. For example, with the monitor concept and condition objects, we've created a buffer class, and we used a condition variable with a with block around that. And if the buffer's full, we wait. If the buffer's empty, we wait. We notify when the buffer, something gets put in the buffer, something's taken out of the buffer. So we've done some stuff with these, but we haven't looked at how do I get one thread to communicate with another one except through kind of that shared object like that. So we've looked at synchronization a lot, not looked at communication a lot. So thread communication, there are several methods, and we've already seen a couple. One of them is that shared memory model, where threads are separate execution streams, but within a single process. So if we're running multiple threads within one process, which is kind of the definition of a thread, that it shares the same process space but has a different thread of execution. But you'll notice that here's a process. Here are multiple threads inside of that, but they all can access the same global variables that we have over here. So in other words, they have their local variables that are maybe inside of the thread function. They were declared in there, created in there, accessed in there. Those are all kind of isolated from each other. But then global variables, they could all access those. So that's where we need synchronization. This thread is accessing a global variable and modifying it. Like, think back to our ornamental garden problem, where you have the count variable lives out here, and then the entry thread says count plus equal 1. The exit thread says count minus equal 1. They're both accessing that shared variable. And then maybe you have a main thread that says read the count and output it that reads that global variable. So any of these threads can access any of the global variables, but we have to do so carefully. And that can be dangerous by just saying, hey, have at it, access the shared variables, global variables, however you want, whenever you want. And that's where you can end up with things like the bank account being corrupted, or the count of the number of people in the garden being incorrect and saying there's -1 people in the garden, or at the end of the day, everybody's gone in and everybody's left, and it says there's still 10 people in there. So that's where we get into trouble, is when we access these global variables. So one of the things, ways we can communicate between threads is by using global variables or shared variable space. But that can be dangerous, and we need to use synchronization to protect that. Now, another form of thread communication we saw were events. And events are kind of that, like a shared flag object. And they can act like a simple shared variable, but they're a shared variable that's either true or false, or set or clear. Those are the only two values you can have for those. And you can wait on them. You could have a event.wait, which will block and wait for it to become true, and then unblock. And so it's a simple form of communication that can also act as synchronization, but the kind of value that you're sharing with one thread and another thread is just true or false. That's it. That's the only value that an event has. So it's a very simple kind of shared variable that's the only Boolean. And so it's very limited with what you can do with that. So what we want is something that's more, I guess, able to share just arbitrary data. So you could have it share whatever you wanted to share. So for example, you want to share some list of data items, or you want to share a whole stream of data items, or let's say it's something like a Google search and it wants to share a whole list of possible search matches and put them up on your browser. So a whole network of machines came up with the search results, aggregated them, put them up, sent them to your browser window. So that's what we want. So what the mechanism we're going to look at today is a thread communication mechanism called queues. And what a queue is, it's a new mechanism. We haven't seen this before. It's not really a synchronization mechanism, although it has internal to it synchronization that makes sure that it's thread safe, that it's synchronized, that it works correctly, that the data is protected in it. But it essentially works like that monitor concept buffers that we created for the previous lab. But it's already done for us. It already exists inside of this object or mechanism called a queue object. All right, so what do those queue objects provide? They provide a thread-safe synchronized FIFO, which stands for first in, first out, meaning that the data that you put in first, when you place data into the buffer, will be the first items that come out. In other words, it's just like a linear buffer that you stick data into and pull the thing out of. Very similar to our producer and consumer relationship that we talked about before. But one of the cool things about queues is that they support any number of producers and any number of consumers. So you can have multiple producers feeding things into the queue. You could have any number of consumers taking things out. And because it's synchronizing it and making it thread safe as an intrinsic nature to that object, we don't have to worry about it. We don't have to create locks. We don't have to create a semaphore. We don't have to create condition objects. We don't have to implement it ourselves. The queue does all that for us. There are versions of the queue that also provide last in, first out, which is essentially like a stack instead of a linear buffer. And there's also what's called a priority queue, which allows us to have the items in the queue be sorted in sorted orders. In other words, you could put things in there where this is item 1, this is item 5, this is item 7, and it will always put them in sorted order, which allows you to create a system where more important things that go into the queue will come out first and less important things can come out later. I'll mention how you create these, but we're not going to spend a lot of time looking at least not today, where you would use those. But just know that you can create a LIFO queue or a priority queue. And I'll show you how to do that, but not necessarily the use case or the pattern where you would use that today. All right, so essentially what it allows the exchange of multiple items or a stream of items between 2 or more threads. Very similar to that paint buffer, finish buffer. And I notice I misspelled finish. It's spelled there as is the country. Let me fix that. We're not talking about Finland here. So from the previous labs, the paint buffer, finish buffer, it works like that, but we don't have to implement that object ourselves. It's something that already exists. And to interact with queues, we can put items in it, and we can get items out of it. And the cool thing about the way queues are implemented in Python is that it can store objects of any type. So it could be a queue of integers, a queue of strings, a queue of game objects like multiplayer objects for a multiplayer game where each player has their own thread and they all communicate to the main server. It could be anything like that. It can be anything. It could even be a queue that has that acts as a buffer of lists or dictionary items or arbitrary objects, anything. All right, so a quick example of that. Queues have that internal buffer that stores a list of objects, essentially. So here's a kind of an example of where you might have that. Let's say we have a message board, and here you can think of something like Discord. And that Discord server has to take messages from a number of different threads where people are talking to it, and it's receiving those messages and then posting them to the message board. So how do you have multiple clients, and sometimes it could be 2 or 4 or 1,000 different clients, all sending messages to this message board, and have them all show up without them stepping on each other's toes, or some of them getting lost or something like that? Well, we could use a queue in between. So here's this queue object. Here are these 2 clients. One of them is placing the message hello ? The other one might be placing this message ASL, and both of those need to show up on the message board at some point. So we stick them into the queue. That's guaranteed to be thread safe and synchronized. And then we pull things out of that. When things show up in the queue, we can pull them out and then show them on the message board stream. Again, think something like Discord. And they show up on the screen. And we're guaranteed, because we're using a queue that is synchronized and thread safe, that messages won't get lost, they won't get corrupted, they won't get duplicated, that we're guaranteed to have them show up. Every message that was placed in the queue will show up and be available to be taken out of that queue. And again, because we can have any number of threads interacting with that queue, you could have just one client over here feeding messages in, or 2 or 4 or 1,000 or 1,000,000, however many you want, can place things into the queue. And in this case, the message board thread is just going to take them out and show them on the screen. So notice this queue is kind of a data object that accepts those connections and then displays to have things placed into the buffer or have things taken out of the buffer. Again, very similar to what we did ourselves with that condition object and the monitor concept that we looked at previously. Okay, so the cool thing about queues, they can have any number of threads interacting with that queue. The queues are guaranteed to be thread safe no matter how many threads are interacting with it. So messages, again, won't get lost, won't get corrupted, won't get duplicated. And because you can have any number of threads interacting with it, that makes it really useful for a number of applications or program systems organizational structures. So for example, you could have a one-to-one that just acts as a buffer between one thread and another thread. In other words, rather than having a shared variable where they have to synchronize and hand off the value, you could the producer sticks it in the queue, the consumer takes it out when it gets to. That's a lot like your computer system and I don't know, something like a keyboard buffer. When you type, they go into a keyboard buffer, the program runs, it takes things out of the keyboard buffer and uses them. But you could also have one-to-many. So you have one thing feeding data to many different threads. So imagine you have one thread producing stuff, feeding it to many of them to process them. So this could have one main program farming out things. And this example of that might be something like, I don't know, like a Google search, where you have one thing that you say, hey, I want to search for this term. And then you farm that out to a lot of different things. But it could also be many-to-one, where a lot of things feed into one thread. Or you could have many-to-many, where you have multiple producers feeding multiple consumers. And that might be like think of like a factory simulation where you have a dozen workers that are producing parts that are then feeding them to the next stage in the assembly line, where all of them get painted. And then maybe those all get fed to the next line. So think of that kind of multiple people working, feeding multiple people using that work for something. But really, any kind of producer-consumer scenario. You have producers, you have consumers, or you want to have data come from one thread and go to or one set of threads and go to some other set of threads. That's a useful case where you'd want to use a queue. All right, so let's look at how it works in Python. So how queues work in Python. This is one of the first mechanisms we've seen that's not part of the threading module. This has its own module called the queue module. And what we do there to use that is we import queue, Q-U-E-U-E. And then from in there, we have to create an instance of a queue. So we just say queue.capital Q. And like most classes in Python, it's capitalized, so queue. That's going to create a queue object. Now, once we have that queue object created, we can now use it. We can put things into it. We can take things out of it. And there are a couple optional parameters here. You can create or one optional parameter, there's a max size parameter you can set. So if you set it to 0, which is the default, then you get an infinite size queue. And it's really not infinite. It's limited by the amount of memory you have in your machine that's running this, available for your Python interpreter. But there's no bound on it that's set by the language. In other words, if it can allocate the memory, and you put something in the queue, it can grow to a bigger size. If it does not and it runs out of memory, you're going to get an exception that gets thrown. But the other cool thing about this is you can also set a maximum size if you only wanted to have a certain number of elements worth of depth in that buffer. So for example, for our previous lab with the paint buffer or the finish buffer, maybe you set the max size to 4. And then that allows 4 things to build up before it gets full. All right, now quickly, I did mention the LIFO queue and priority queue. How do you create instances of those? Well, that's not any different. It's just you use a LIFO queue or you use priority queue. And again, the main difference between those, the LIFO queue acts like a stack. In other words, last in, first out. And the priority queue, basically, as you put objects into that buffer, it sorts them. And there are ways to change how that gets sorted. We won't worry about that right now. But note that to use the queue, we have to import that queue module. Import queue, queue.queue creates the instance. And then once we have the instance, we can use it. Okay, well, how do we use it once we have one? Let's take a look. All right, so this should seem familiar, but you use .put and pass in some item. And this item here could be any object. This could be an integer, it could be a string, it could be a reference to some object, but that's putting that item into that queue. How do you get an item back out? Q1.get. So this puts it into the buffer. This takes the oldest thing, the thing that's been in the buffer the longest, and pulls it back out, and it returns that. Now notice these have some optional parameters as well. You can set this to, by default, blocking is true, meaning if you try to put something to a full queue, that put will block. If you try to get something from an empty queue, that will block. But you can set that to false. Or you can also set a timeout and number of seconds to wait to try to put something or get something. And these are available just so you can set it up so it blocks and waits, but only for a certain amount of time. So your Perl program doesn't necessarily lock up. And you could check to see whether that actually gave you a value or not. Now, this q1.empty returns either a true or false if it's empty. q1.full returns a true or false. It tells you if it's full. So you could check before trying to get an item. You could say, hey, if the buffer is empty, don't try to get anything. If the buffer is not empty, get whatever's in it. So this is another way without setting blocking to false. So you could say, only try to get from a buffer that has something in it, or only try to put something into the buffer if the buffer is not full. Now this q1.taskDone, that's going to be used by your consumer threads, and each time you call get and get a reference to that object, you should call taskDone after you've done the get, and that tells essentially what that does is it informs the queue that now I'm done with that object and I've done processing it. And the main reason for that is for when you use a q.join, which q.join will block on that queue until everything has been pulled out of the queue, but not just that, everything's been pulled out of the queue, and we said we've completed all the tasks. We've done a task done on each. So this makes sure that when q1.join continues and unblocks, that not only have we pulled everything out of that queue, but we're done with processing that data. And that could be useful for us to know, when do I know to go on? Well, once somebody's pulled everything out of the queue and they're done processing it, they're done with that data. And we get to explicitly say that with this taskDone method. All right, now, since queues potentially allow many consumers, that means they can be used to feed tasks to some number of worker threads. So for example, you might have a number of threads. There's a thread pool thing we're going to look at later on. But imagine you have a bunch of worker threads and you want to farm out tasks to them and say, okay, you're thread number 1, you're going to I don't know, you're going to handle, imagine it's like handling a multiplayer game. So let's say you have 10 worker threads, and you're like, you're going to handle player 1, you're going to handle player 2, you're going to handle player 3. Or maybe it's non-player characters in the game. You say, I'm going to farm you out, you're going to calculate the decision that this knight is going to make, you're going to calculate the decision the wizard's going to make, and it's doing some sort of AI. But notice that you can feed tasks to those worker threads to have them then process that and then give you an answer back. Or you might have a number of producer threads feed into a single consumer thread, like the chat server example we had before, or maybe a distributed logging system where you have a whole bunch of threads in your program all making log file entries that need to be tracked. So if something crashes, you can look at the log and know, hey, what threads were doing what at what time. And that's some uses for queues, kind of that single thread feeding multiple worker threads, or multiple producers feeding data into one single aggregator. And so that aggregating results can be an important part of how to use these queue objects as well. So let's take a look at that. So to aggregate results, the idea is that threads, you may have noticed when we were using them, they kind of, you start a function. So you say like target equal and you give a function, but there's no way for them to return a value. So threads don't return a value because where would it return it to? There's not really a function call that happens when you start a thread. You say start the thread and then let it run. And so if you have a case where you want to spawn off a bunch of worker threads but have them give you back an answer to something, sort of like a distributed computing, or you divide up a task, give everybody a little bit to work on and say, hey, report back to me the result of the work you did. Well, the problem with that, with the thread not being able to return a value, is we need some way to get a result. But we can't just use shared variables for that easily. We won't, because we might have a result of one override another one. So a queue is a really useful way to do that. So each worker thread gets spawned. The arrow going over this way is us spawning that thread. It then does its job and it returns a result back to us. But we want the main thread to capture all of the results from all of the workers and then maybe come up with an overall result from that. So how do we do that? Well, one of the ways to deal with this is to make a queue object that all the results go into. So we can guarantee we get all of them that came back in. And so if threads can't return values, how can we collect the results? Well, we use a queue. Each thread puts its result into a queue. The main thread then reads all of the results out of that queue and then does something or further processes them. So in this case, that's many producers producing results and one consumer, the main thread, consuming that. And realistically, you could break something down even further. Like when you do a Google search, maybe you pass something divides it up to a bunch of worker threads. And let's say this one's searching part of the internet, this one's searching a different part of the internet, this one's searching a different part. And then maybe they'll divide it up across other threads on other machines, and they'll divide it up. And then eventually the results come back with a score. And this one passes back maybe the top 10 that it had. And then this one gathers the top 10 of all of these, and then it sorts them. And that's what shows up on your browser screen. And so you can kind of see how a queue would help, because you need some way to aggregate and pull all of those results back and then do something with them. And that queue gives like a single mechanism that everything can go into that's guaranteed to be thread safe, synchronized, and avoid corrupting data or missing things. So queues can be really useful. Let me go back. All right, so here's how that would work out in the actual, this is not real code, this is pseudocode. But here's a worker thread. A worker thread would process data, and then when it has its result, it just puts it in the queue, and then it's done. So compute answer, put your answer in the queue, exit. So the main thread would look like this. So you say, hey, for I in the range, however many worker threads we want, start a thread for each of the workers, and then wait for all of them to finish by using a join for all of the workers. And then after that, just go through for the number of workers that ran, because we know they've all finished now. We know they've all placed their result in the queue. So now we have a for loop that just goes through, get the result from the queue for each one of the workers, and then maybe does something with that result. So you can see here, all the workers are going to be started. All the workers are going to be finished at this point because we're joining with all those threads. And then we will get all the workers' results because the last thing they did was put their result in the queue. Now, there are cases, certain cases where we want to start a worker thread and have it run and consume data and use things we send to it until we tell it to stop. And the way to accomplish that is by establishing some special message that we're going to send to the worker that tells it when to stop or when to halt. And those special messages in cases like this are called a Sentinel message. So in other words, you might say, hey, I want you to start working, and I want you to work till I tell you that we're done. And the worker thread can just sit there and work and work and work and work and work, and then you say, hey, stop now. And when it gets that stop message, it's going to stop. So in Python, it's common to use none as the Sentinel value. So in other words, like, here's your data I want you to work on, and it gets, it's like, this is nothing. I'm going to quit. So here's what that would look like. So here's a worker thread, and again, this is pseudocode. You say while true, so this is going to run forever. You get something, a message from the thread. If it's none, we break out of the while loop, which then completes. Otherwise, if it was a real message, we process the message and do whatever it is we're going to do with it, use it, and then we go back up to do another get. If we ever get none, we quit. This thread exits. So this thread will run forever until it gets this special Sentinel value of none. So the message processing loop will run forever or until somebody puts none in the queue and it gets none out of that queue. And let me fix one thing here. I suppose it should be Q1 to match the rest of the stuff. I don't know why it says G1. So when it gets that special Sentinel message, that can break the loop. Now, it doesn't have to be none. You can put other things. You can put a string that's like quit or stop or something else. Or you could even put something in there that basically says, hey, if after I did that get, if the queue is empty, we could do Q1 dot empty. And if that's true, break. We could do it when the queue runs out of things, we exit. But there are cases where the queue will run out, but we still want the worker there, so we can put more things in. It can process them, put more things in, process them, put more things in, process them, and then say, okay, stop. Here's none. And then it knows to stop. All right, so quick summary of queues. What's the motivation? Well, using shared memory for thread communication can be dangerous if we're not protecting it with synchronization mechanisms. And we have to make sure we're using those synchronization mechanisms properly, like we did with that monitor concept with condition variables. Events are guaranteed to be safe, but they don't allow us to communicate anything other than a true or false value. So those aren't real general purpose. But queues, they're safe, they're flexible, meaning you can use them for one-to-one, one-to-many, many-to-one, many-to-many, all kinds of relationships between any number of threads. They'll work on any number of threads in any configuration we want and any type of data object. So queues are really useful for inter-process communication, or inter-thread communication in this case. They can also act as buffers when they can either be unbounded, meaning infinite size buffers, or we can make bounded buffers. And if we need to, we have a stack version of that in a LIFO queue. We have a sorted version of that in a priority queue. So they're pretty useful things to know how to do. So if you need to communicate between two or more threads, you probably want to consider using queues and rather than doing it yourself, because it's already done for us and it's guaranteed to work and be safe. You can always, if you have special needs like the bank account thing we did where you want to create a monitor methods around the bank account and logging or whatever, then you can still design your own using your own condition variables. But queues, as far as a general purpose communication mechanism from one thread to another thread, or from a number of threads to one thread, or from one thread to a number of threads, or a number of threads to a number of threads, it can be a really powerful and easy to use mechanism for inter-process or inter-thread communication. Okay, so that's all for today. Relatively quick lecture, only a half hour. You should be working on your labs and getting those done, meaning that you should already have done the the lab with the factory simulation thing. That one should be done. You should be working on the ones after that. For example, the file downloader, the multi-threaded file downloader for doing I/O bound processes. You should be working on that one. I'm not going to give you a new lab today because I want you to get caught up on those other things. But next class, we're probably going to cover some more stuff, and then we're going to move on and have another lab. So until then, everybody stay safe, stay warm. If you have to go out somewhere, be careful. Roads are icy. Hopefully, it's supposed to get warmer later in the week. Hopefully, it all melts off and we can get back to a normal schedule. But until then, stay safe. Wear a mask, wash your hands, or just stay home. And I'll see you next time. Let me know if you have problems or questions. Send me an email. Send me a text message. Get a hold of me. I'm happy to help. That's why I'm here.